Hello, can you hear me? In the last class, while I was taking the class, we got disconnected due to network issue. So can you tell me
Yes, sir.
can you tell me the topic that you are discussing? Topic means until which part we have completed. Shall I repeat the last class? If we got disconnected early, then I think we should repeat the same class because most of you are not able to get the topic very well. Okay, so we are talking about minimization of objective function. Minimization of objective function j theta. Okay, so j theta here represent the error function for logistic regression, and when the error will be found to be large, then we need to minimize the error so that we can get the error to be minimum. Okay, so to minimize the j theta or the error function, we can apply the optimization. We can apply the optimization. Now, what is if we employ the optimization technique to minimize the error, then actually we are solving j theta. So solving j theta means we have to make the gradient of j theta. Okay, gradient of j theta should be 0. So what is gradient of j theta? Gradient of j theta means we will take the derivative of j theta, okay, and that to be make 0. So in this way we can minimize the error function j theta. Now to solve the j theta, we can consider two different types of function. One is called univariate function, and another is multivariate function. Now, what is univariate function? So all the univariate functions will be having a single variable. Now, for example, if we write y equals to e to the power x, okay, e to the power x, then this univariate function y equals to e to the power x can be approximated by Taylor series. Okay. Now, there will be some functions which will be infinitely differentiable and continuous. So they are found to be very complicated function, and for these complicated functions, we can use Taylor series approximation. So this Taylor series approximation, okay. So this Taylor series approximation can be used to approximate such infinitely differentiable and continuous functions. And so here univariate functions can be approximated in terms of first order polynomial approximations, okay, and second order polynomial approximation. So if we use the first order polynomials to approximate the function y, then the first order polynomial will approximate the function at some point p as straight line tangent. okay, at straight line tangent. Now if we get the functions, let's say the functions that we are getting like this. So this is the x-axis, this is y-axis, this is our 0, okay, this is 1, 2, 3, this is 1, 2, 3, and so on. This is -1, -2, -3, and so on. Okay. Then we can approximate the function y equals to e to the power x at point P. So this is the point P, okay, at which we can approximate the function as straight line tangent. So this is the straight line tangent. An equation may be y equals to 1 plus x. Okay. So y equals to 1 plus x. With this straight line tangent, we can approximate the function y equals to e to the power x at point P, where where we can find the function y equals to e to the power x is differentiable. Okay, that means at point P we can find the function y equals to e to the power x is differentiable with this approximation y equals to 1 plus x. Okay. Now this is the first order polynomials that we can use to approximate the function at some point P, where the function is found to be differentiable. Now we can have another choice. Another choice means if we get the second order polynomials, then how the second order polynomials can be used to approximate the function at the same point as quadratic equation. Okay. So we get the same function over here. This is our 1, 2, 3, and so on. This is 0. This is y equals to the power x. Okay. So here how we will get the approximation. So we can get the approximation as quadratic equation. So quadratic equation, the equation may be y equals to 1 plus x plus half of x square. Okay. So this is the quadratic equation. So with this quadratic equation, we can approximate the function y equals to e to the power x. So when we use the second order polynomial, okay. So if we use if we use higher order polynomials, then the approximation will be better than the better than these two better than these two straight line tangent and quadratic equation approximations. Okay, so we can have the different choice in cubic. So we can get the cubic equation, we can a quadratic equation. So those will be found to be better approximation than straight line tangent and quadratic equations. And if we consider the multivariate functions, so multivariate functions all will be having more than one variables. So in to approximate such multivariate functions, we can represent the Taylor series in terms of Jacobian and Hessian matrix. In terms of Jacobian and Hessian matrix. Now, primarily we are interested to talking about optimization techniques, and in optimization techniques we are interested in gradient descent. Okay, so what will be the background? What will be the background idea from which we can derive the gradient descent equation, and that will be used to optimize or minimize the error function j theta. So that is the whole idea we have to discuss. Now let us consider the Taylor series. So this Taylor series is used to approximate a function fx at point P. Okay. So we can write fx equals to fp plus f dash p into x minus p plus half of f dash f double dash p x minus p one upon n factorial f n p x minus p to the power n. So this is the infinite. So here we have infinite terms in the Taylor series. Now in summarized form, we can write fx equals to summation n equals to 0 to infinity over 1 upon factorial n fn of p x minus p to the power n. Okay. Now, if we consider univariate function, any univariate function fx, then in this univariate function there will be only one variable. Okay. Now, if we write the univariate function fx equals fx, okay, fx plus, let's say we are writing fx plus delta x. Okay, we can write fx plus delta x. Okay, we can write df by dx. We can write half of delta x square d2f dx square. Okay. So if we consider first three terms of Taylor series for univariate function, then we can write f of x plus delta x equals to f of x plus delta x into df by dx plus half of del x square into del 2f by del x2. So here we are considering first three terms because we have to approximate both univariate and multivariate functions using Taylor series expansion. So therefore, we need to consider only the first three terms, and these three terms are sufficient to approximate any univariate or multivariate functions. So here thing is that we have the interval del x, and we have only one variable x. Okay, we have only one variable x. Now here we can write that here delta x is the interval. So here we can say that delta the interval. So what is interval? So interval is the deviation, or interval is the deviation between the current point and the future point or next point. Okay. So we get the deviation. So if we get the next point x k plus 1, then and the current point is xk, then we get the deviation between, or we get the difference between the next point and the current point, and that will give us the interval del x. Okay, so here del x is the interval. Now let's say we are having n variables. Okay, instead of having one variable, we are having n variables. So we are considering the multivariate function. There will be only one function, but in that one function we are having multiple variables, more than one variables, instead of only single variable. So here we can get x equals to, we can write x equals to basically x1 x2 xn. So we have n number of variables. So for n number of variables we will have n number of intervals. Okay, so we can write del x1 to del xn. Now for n number of variables and n number of intervals, we can write the Taylor series for first three terms as x plus del x. Here del x is the vector, not a scalar. Previously we found del x is the scalar as well as x the variable, single variable is scalar. Both are scalar. Now we are considering there are n number of variables x1 to xn, and uh, there will be a corresponding x number of intervals del x1 to del xn. Now for n number of variables, we can rewrite this Taylor series for first three terms as f of x plus del x. So here del x is the vector, x is also vector. So we can write f of x plus del x equals to f of x plus del x transpose. Why del x transpose? Because we need to get the dot product between vector del x and the gradient f. What is gradient f? Gradient f of x. Okay. And here we will write half of, for the third term, we will write half of del x transpose. Okay. Here we will write h, and which is multiplied to get the dot product between h and del x. Okay. So instead of writing del x square, because del x is the vector, so therefore we get the dot product between del x and h. So this is the Taylor series for the first three terms when we are having n number of variables and the corresponding n number of intervals. Okay. Now what we call this h? So here h is the Hessian matrix. So for Hessian matrix we can write h jk equals to, we can write partial derivative del f by del x j del x k. Okay, so Hessian matrix is symmetric. So we can write hjk equals to hkj. Okay, we can write this because Hessian matrix is found to be symmetric. So therefore, for the single variable as well as for the multiple variables, we can get the Taylor series expansion for the first three terms. Now let us consider there are n number of functions. Okay, now we will say there are n number of functions. So we can write f1, f2 until we will get fn. So there are n number of functions. So here we have n number of functions. Now we are having n number of functions. Okay, n number of variables, n number of variables, n number of unknowns. Okay, n number of variables. So for this, we can write f equals to del f. What del f? What del f? So del, previously we have seen that this del f is nothing but the gradient of fx. Okay, if fx is a function, whether it is univariate or multivariate, so for the multivariate we get del f, we get del f x as the gradient, and we can write small x, small f equals to del capital F. So del capital F means what this will give. So del capital F means this is the gradient. So gradient means here we will get a vector. Vector of what? Vector of partial derivative. So partial derivative over with respect to this n number of points. So we can write del f by del x1, del f by del x2 until we get del f by del xn. Okay. So now we are considering n number of functions. Now we are considering n number of functions. Instead of considering just one function, we are considering n number of functions. So here we have n number of functions, n number of variables. Okay, now we are writing small f. This small f is the set of n number of functions. So we can write small f equals to del f, and this del f will give us a vector of partial derivative of f with respect to n number of points. Okay. Now for these functions, what we can write? We will write f of x. Okay, f of x will write f of x plus j. What is j? What is j? So j is known as Jacobian. Previously we got Hessian matrix. Now we get Jacobian. Jacobian matrix. Okay. Now we got Jacobian matrix. Okay. We get Jacobian matrix. So okay. So now let us consider, since we have to solve the function f equals to 0. So we can write 0. Okay. And let us consider we are writing f of xk. Okay. What is Jacobian? So we can write jk equals to del fj with respect to xk. Now what is so that means we are considering jth function. Okay, and here we are considering xk point. That means we are getting the partial derivative of jth function with respect to xk point or xk variable. Okay, so this is Jacobian jk. Now since we have to solve this function to minimize the function, objective function. So here we are writing 0 equals to f of xk minus, here we are writing j of xk. Okay, so here we get actually del x. Okay, since we are considering n number of variables and we are having n number of functions. Okay, so we are writing f of x equals to f of, okay, f of x plus del x. So f of x plus del x equals to f of x plus j into del x. Okay. Now del x, what del x represent the deviation between the current point and the next point. So here we will get xk plus 1 minus xk. So this is the next point, and we have to working on that, because if we start from the current, if we start from any random point xk, so we have to find the next point. Okay, we have to find the next point to solve this equation. So we can write f of xk plus j of xk. Okay, we get the Jacobian at the current point xk, and then we are writing this del x in terms of xk plus 1 minus xk. Okay, now we will rearrange this equation and we will get xk plus 1. So we are writing xk plus 1 minus xk on the left hand side, and on the right hand side we are writing f of xk by j of xk. Okay, so here we can write j xk inverse. Okay, jxk inverse into f of xk. So therefore we get xk plus 1 xk j xk inverse, okay, f of xk. So we get the next point. If we start from any random point xk, okay, xk is any point from where we can start to optimize the function or minimize the objective function j theta. So this is the point from where we start, and we get the next point xk plus 1, which is given by xk. Xk is the current point, okay. So xk minus jxk inverse into f of xk, okay. Now let us take an example, and after which we will write the equations for Stefan's distance and Newton's method, and then we will try to explain that if we use the Newton's method, either Newton methods or Stefan's distance, so how we can get the convergence for minimization of the objective function, okay. So here now let us consider a function fx equals to x square minus 9. So we know what will be the root of this function, but since we need to understand the idea behind gradient descent, so we will look into this, and we will try to solve this function, and in terms of Jacobian, and then we will try to establish that if we have Newton's method for optimization, then we will converge quickly towards get the optimal value. Okay, so now we are writing xk plus 1 xk minus j inverse fxk. Okay, so what we will write x xk. What is j xk inverse? This is the first order derivative. Jacobian means the first order derivative, okay, and Hessian means the second order derivative. So here we get the Jacobian of the given function fx. Okay, so here we will write 1 upon, so j inverse, so j xk inverse 1 means here we will write 2xk, okay, which is multiplied by x square minus 9. So if xk is given by xk square minus 9, okay. Now we are writing 2xk square minus x square plus 9 to xk square, okay. Now if we take, now how we can represent this? If we write this, if we get the minus so what this will give us? So this xk plus 1, we are getting xk plus 1 equals to 2xk square. So here we are getting actually xk square plus, so plus 9. Okay. And 2xk, 2xk. Now, if we rearrange this, if we rearrange the terms on the right hand side, then we will get some multiplier over here, okay, and something we will get over here, like this. We will get if we rearrange the, so xk plus 1, like this. Now, from here we can easily say that the root of this equation will be 3. That means at x equals to xk equals to 3, we will get the function is derivable. We will get the function is derivable. That means at this point xk equals to 3, the function to be optimized. Okay, function to be optimized. Now, since we are getting, so if we want to further want to check whether at point xk equals to 3, whether what will be the error function or what will be the error of this function, then we can get the error as square form. Okay, square form. So which is nothing but the Newton's method. In Newton's method, what we get in Newton's method, we write xk plus 1 equals to xk minus Hessian. Okay, and here write del f x, del f x. Okay, what is del f x? So del f x, see here, this is the Newton's method. If we look at the steepest descent, now steepest descent mean, so we get the steepest descent method xk plus 1 equals to, which is given by xk minus s l fx. Okay, this is the steepest descent. Now, if we look at both this method, Newton's method and steepest descent, so we can see that the steepest descent, steepest descent method get this s, which is multiplied with the gradient of a given function fx. Okay, so gradient of given function fx, and this s is known as step size or learning rate. Step size or learning rate. Learning rate. Okay. So how we can interpret this steepest descent? So here we are taking the scalar step size or learning rate, which is multiplied with the gradient of given function fx. So that means we are moving towards steepest direction of gradient of function fx. Okay, that means this gradient of given function fx will give the direction towards the convergence in terms of this steepest descent direction. Okay, so steepest descent direction, moving towards steepest descent direction is nothing but moving towards the gradient of the given function fx. Okay, and to converge towards some optimal value, so we get this learning rate or step size. So this will decide how much step we should take along the steepest descent direction, or the direction towards the gradient of the given function. So this s will, since the s is the scalar value, therefore this s will decide the step size whether we can go fast or whether we can go slow. So this will decided by this step size of landing rate. But this will sometimes this will not give the right direction, or sometimes we don't converge. Sometimes we get stuck in the local minima. So therefore, sometimes we found that Newton's method is outperforms the steepest descent. Okay, so what is the properties of this Newton's method? If we look at the properties of the Newton methods, then we can see the error gets squared. Okay, that means the convergence is speed up in Newton's method. And to get the correct direction, we get first we get the Hessian. So here we are writing xk plus 1 given by xk minus h inverse, which is multiplied with del fx. And this del fx is nothing but the gradient of the given function. That means previously we computed Jacobian matrix. So Jacobian, we can say the Hessian matrix is the Jacobian of gradient of the given function. So Jacobian of the gradient of the given function will give us this Hessian matrix H. Okay, and since here we are getting the error is determined as squared form, so therefore the Newton's method will found is found to be speed up towards the convergence. And we will be interested to apply these Newton methods over this steepest descent in our optimization problems. Okay, so we will have to decide what will be the hypothesis representation, and from there we have to compute the error objective function as error function for a classifier, and then we will optimize that objective function or the error function in terms of gradient descent or any other optimization technique. If we go for gradient descent, then certainly we will have two different choices, Newton's method or steepest descent. So if we go for Newton's method, then we will maybe we will converge quickly towards optimal value. Otherwise, we have another choice. We can apply steepest descent, and with this steepest descent, we can we can go towards the optimization for convergence. So this is the whole idea behind the minimization of objective function j theta. So there are a few steps that we have to remember. The steps are that the first step is we have to determine the hypothesis representation, and then we will decide we'll decide what will be our error function as objective function. And if the error is found to be very large, so we have to iterate that objective function, and we have to reach to the optimal value where we will get the function is derivable. And for that optimized value, we will get the objective function to be minimized. That means the overall error will be found to be minimized. If you have any questions, you can ask me. So that's all for today. If you have any questions, you can ask me. Otherwise, tomorrow you will start a new topic. Okay, that's all for today.